Hello everyone, welcome again to our channel. Today we're going to study a very interesting topic concerning the model of individual risks applied to your previous knowledge on actuarial mathematics for life contingencies. We hope you enjoy it. Okay, let us suppose we have a portfolio with 60 whole life insurance contracts for 40-year-old people with a benefit of 1,000. With the use of the inverse transform technique, as well as the Monte Carlo technique, we will find the least k such that the probability of ruin is less than 5%. If the company charges a term insurance due to omega minus x years of a person of age x, plus k times the square root of the variance of the random variable set. Suppose that the discount rate is of 3%, and mortality follows the mortality table MMEX 8289. We need to find the premium we will charge to each policyholder. We can see this in another way around. Suppose that instead of having a whole life insurance of a person of age 40, we have an omega minus x term life insurance of a person of age 40. And given that the maximum age is 100, thus, we will be working with the following notation, which is a 60-year term life insurance of a person of age 40. For you to understand it better, remember that an n term life insurance covers the death of a person of age x in a lapse of n years, and if this person dies within that time, which is x and x plus n, the insurance company will indemnify the benefit at the end of the year of the death. Given that we have a portfolio with 40-year-old people, we must focus now on age 40, and with the help of the mortality table, we will start to compute the present value of the random variable set of an n-term life insurance, which is given by this next formula. It is the sum from k that equals 0 up to n minus 1 of kpx times qx plus k times the discount factor.
So now we are going to start by computing KPX, which is the probability that a person of age 40 survives the next k years. This is why we have KP40, where k takes the value of 0, 1, 2, 3 until 60. For that, it is important to recall the formula. This is why we play it here in the presentation. Please notice that the probability of a person of age x surviving 0 years is equal to 1, because it will be exactly the same as if we are asking for the probability of a person of age x being alive right now. Here you have the formula, and you can see that in fact kpx is equal to 1. Now, with the help of the following binomial 3, we are going to make sure you understand the process of obtaining the oncoming probabilities and the reason why we need to accumulate them. Remember that in order to survive k years, one must survive k minus 1 years, and the previous one. In other words, the probability of surviving, let us say for example 2 years, is the probability of surviving 1 year at age x times the probability of surviving 1 year at age x plus 1, and so on and so forth. Here you can see the binomial 3. Thus, we need to accumulate the following probabilities. Here in the video you can see how. Now, we can proceed with the calculation of KP40 times Q40 plus K, which in other words, it is the probability that a person of age 40 survives k years and dies in the next year, which actually talking is understood as follows: K defer Q40. In the next column, we are going to calculate a discount factor for each k plus 1 year, which is given by the next formula, where the interest rate is equal to 3%. can proceed to calculate the actuarial present value of the random variable z, which we can compute in 3 ways. The first one is by doing the product sum of column F with column E. The second way is by a recursive form. Here you can see the formula. And last but not least, we created a Visual Basic program. Here you can see the program, which is called AX1N, and this function asks us to put the age, the term, and the discount rate.
Then we calculate the variance of the random variable set, and for that let us remind us that the variance of set is equal to the expected value of set squared minus the square of the expected value of set, which in other words is the next formula that represents the actuarial formula. First, we elevate the F column, which contains the discount factor column, to the second power. Then the sum product of the H and E column minus the AX1N previously obtained to the raise of the second power. Or we can simply compute this with our function AX1N, but instead of putting the discount rate of 3%, we are gonna raise it to the second power minus 1. For the premium, it is simply the actuarial present value of set plus k times the square root of the variance set, but we don't know what k is, and for that we are going to suppose it is 1 until we find the k that minimizes at least until the 5% the probability of win. For that, with the help of the inverse transform technique as well as the Monte Carlo technique, we are gonna find such as k. In the next column, a counter will be served to see how many simulations we have computed. Next, with the normal inverse function, we will obtain the random loss of the portfolio containing 60 policyholders, and in the next column, we subtract from the random loss 60 times the premium, and this is how we obtain the actual loss of the portfolio. Is there win? If the loss is larger than the random loss, we ask for a 1, if not a 0. Simulating this process numerous times, we can see that the probability of loss is 0. With a benefit of 1, we are charging each policyholder 0.53 cents, which is extremely high. But what if we charge the K and see how the premium is modified as well as the probability of loss? Let us suppose we have a K of 0.2. We can see how the probability of runs is bigger. We can approximate a K such as the probability of run is approximately 5%. Please note that the column containing the random number which we compute with the int point norm will only give us an approximation, and certainly the theorem of the central limit states that if we take a large and sufficient quantity of random variables, then the sum will distribute as normal. But in this case, we are only taking 60 random variables, which are our total policyholder in our portfolio, and for that we are going to create a function that will calculate the probability of win.
This function counts how many ages we have. By this, we mean all the ages or people contained in our portfolio or database. For example, if we have a database from a company with 60 employees, the function intpop will be equal to 60 people. Now, you can see that we have used a function called ubound. This function means upper bound. which gives us the last index from the matrix called ages. And this one means we have to work with the first dimension. So we will work with the last index from the first dimension of the matrix named ages. Our single net premium, P and U, equals 0, and we start a fourth cycle in order to simulate it according to the total number of policyholders in our portfolio. In this cycle, what we do is to call a person of age X and generate the probability distribution for that person. And for that, we have created another function called GenDist. What this function does is that it will calculate the support of the random variable and will give us KQX. This means the probability for a person with age X lives at most K years. For K equal to 0, 1, 2, and therefore until W minus X, where W is omega, is usually the last stage of the mortality table. We certainly expect to have a column with 0qx, 1qx, and therefore until W minus x qx, where this is a distribution function. Next, we call the function previously made of the actuarial present value of the random variable c, and for the deviation, which equals the square root of the variance of the random variable c. Secondly, what we have in the next variable represents the accumulation of the single net premiums of all the people. For the accumulation, we'll provide all of the functions above. Why do we need to accumulate? Well, we need to check if what we have is enough to pay our obligations. Please observe this variable is made up of the accumulation of the insurance of each of the people plus the number of sigma we specified multiplied by the deviation we just calculated in the previous line.
Now we ask the program to tell us the k times entry of the present value of the population. This is done with the next function called VVPPX, that is the present values for a person of age X. So the function VPPOP of X will be called for each of the people. The function VVPPX is a function we previously did. What does this function do? Firstly, please observe that this function gives us a variant. As we can see in the last line, it will give us a matrix. For j equals 1 to the number of simulations, every simulation will give us 1 divided with 1 plus the interest rate, and that elevated to 1 plus a random value. So, we need to give the program a distribution table besides the previous function, called hd, which is the inverse transform. This function generates a random number between 0 and 1. Then, we look up for this number in the distribution table and return the value in the second column. Our purpose is to compare our financial present value of each simulation and what we will supposedly charge each person. So, VPPOP of k is a vector whose inputs are vectors. This is the principal and most important idea of the program. Now, we accumulate the present values of all the people for each simulation and compare it with the single net premium. If the accumulative, that is the sum of the claims, is bigger than what we are supposed to charge, we are ruined. Then we apply Monte Carlo, accumulating a 1 if we are ruined, or a 0 on the opposite case. Later, we calculate the variance of the Monte Carlo's average, and we use it to calculate the left edge of the confidence interval with 95% of probability and also the right edge. Finally, the function will return an arrangement. As we can see, the final result diverges between the program's result and the central limit theorem result. To avoid this, we can increase the number of simulations or we can increase the value of k. For example, if we increase the value of k, as you can see from 0.216 to 0.28, then we calculate a new premium. How? Well, it's the same process as the other premium, but using time sigma. Finally, we calculate the variation of the two premiums by subtracting the premium to premium 2 and then divide it all with premium. Thank you very much for watching this video. We hope it was of great use.